I'm going to be talking about dark halo response in MaGICC simulations, and I'll explain what MaGICC is later. So this is work done with quite a few people, and I want to highlight Ariana De Tintio, who's a PhD student in Madrid, who wrote a paper which I'm going to present here. Okay, so this is going to be just a theory talk. I'm not going to have any data or comparisons to data. So the goal is a theoretical prediction for the structure of dark matter halos. Okay, so why should you care about this? Well, it's kind of obvious, really. So one reason is if you want to constrain the nature of dark matter using galaxy scale observations. So for example, the dark matter density profiles. Also, there's the issues of the satellite mass functions and the halo shapes. I'm also interested in understanding galaxy scaling relations that link dynamical quantities with photometric quantities, like the Tully-Fish relation, Faber-Jackson, and fundamental plane. Okay, so how does theory predict dark matter structures? So there's three ingredients. Obviously, you have to put in the type of dark matter, whether it's cold dark matter, warm dark matter, self-interact dark matter. We've heard about these already. You need to put in the cosmological parameters. These can have quite a big impact on the structure of dark matter halos. And then the third thing is you need to understand how dark halos respond to galaxy formation. So the first two things you can, well, I would say it's relatively easy to simulate. I know we've heard today that there may be some issues. Basically, you can use dissipationless n-body simulations, and there's been a lot of work on this over the past decade. And these simulations can make very precise predictions for the structure of dark matter halos as a function of cosmology. So this is so basically there's two generic predictions. You have these cuspy dark matter halos, and they're specified by two parameters. In detail, they really need a third parameter, but we'll just stick with the two, the concentration mass relation. So we showed with Andrea Macchio that the concentration mass relation, the 0 point, is actually quite sensitive to cosmology. So this is just going from the doubling up first, fifth, and third year cosmology. And just by the little variations in sigma rate, power spectrum slope, and matter density, you get a 50% change in the concentrations of dark matter halos. So the thing you should be asking about these simulations is, I said they're precise, right? When you say that, the obvious thing is, are they accurate, right? Are they giving us the solution to the problem we want? So what about dark halo response? So I'm going to have a little quiz here. How do people think dark matter halos respond to galaxy formation? Okay, so you can. Okay, well, so I'll give you some ideas first, and then you can make up your own mind. So we knew a long time ago, George told us that if galaxy formation is smooth and slow, then halos should contract roughly adiabatically. And this is just based on the idea that if you have a particle moving on a circular orbit, it conserves its specific angular momentum. And you can write that as just r times mass within some radius. Okay, so this is contraction, so the dark matter density increases, and it can increase by an order of magnitude. So this is great if you want to detect dark matter annihilation, say in the Milky Way, because that goes like rho squared, and so you have an order of magnitude or two increase in density, you get factors of several orders of magnitude in flux. Okay, so, but that's not the only thing that can happen. You can also have expansion. And so one of the processes that can occur is dynamical friction. So you can have dynamical friction between baryonic clumps and dark matter halo. It can either be in the form of clumpy accretion or baryon-rich satellites, or it can be due to galactic bars. So this was done originally with just some sort of toy numerical simulations, but it's also been seen to occur in cosmological simulations. So the other process is outflows due to feedback. And it was shown, ironically, in the same year with the NFW famous papers that actually that universal prediction isn't so universal. But I guess the idea here is if you remove half the mass from a bound system, it becomes unbound. And so if you slowly slink baryons adiabatically to the center of a potential well, and then you move them out quickly, then the halo will expand. The problem is it's just not that efficient at creating cores. And so something Justin did was he figured, well, rather than do this just once, why don't you do this several times, right? And then each time you get a little bit more expansion, and you end up with a plausible way to make coarse and dwarf galaxies. And then something which is sort of related to this, it kind of extends from one outflow to several outflow to basically the whole potential is just blobbing around all over the place. And that actually was shown in the movie earlier. So these are some processes that will be occurring in galaxy formation. Things we don't really know which processes dominate. So back to the question, how do Darkman halos respond to galaxy formation? So I'll give you multiple choice so you can simplify it for you. So one option is they don't. All we need is dissipation of simulations. And maybe I should add UC Irvine here as well, because it seems they don't believe anything changes. OK, so the other option is contraction, roughly adiabatic, although not exactly as the M of R formula. So this is based on hydro simulations. And then, of course, the other option would be expansion. This is me in 2006, me in 2012. Different glasses, different mountain, but the same result. This was for late types. This was for early types. Well, I only had 2 papers on this, actually. So what do people think? A, B, or C?
C. Everybody thinks you're right.
No, I'm wrong. No, the actual answer,
Depends on the system.
Of course, it's none of the above. It's well, if I get this thing to work, it's D. It's right. All of these things happen, but I want to try and convince you that they happen in a predictable way. Okay, so there's 2 approaches you can take to modeling this. One is the analytic approach, and the nice thing about this is that you can make realistic galaxies. Okay, you can put all the physics in, you make your spherical approximations, and you can get realistic galaxies out. That's the approach I have been usually taking because I want to make realistic galaxies. The other approach is to do a cosmological simulation, fully cosmological, with all the bells and whistles, the star formation, the feedback, the 3-dimensionality of it. And I guess this is I guess maybe it's not exactly the problem because there is still the subgrid stuff that goes on. But the problem with this method is that most of the time, and I think it's probably fair to say that these simulations, they were overcooled. The simulations were not making realistic galaxies, right? So if you don't make a realistic galaxy, what exactly are you going to learn about a process? What you learned is what not to do. But recently, the MaGICC project has been making simulations that are actually quite realistic. And this is on scale, halo masses from 10 to the 10 to just about the Milky Way. So now, actually, we can go to these simulations and we can look at how the Darkman halos are responding. So I'll just introduce the MaGICC project. So this is something which is happening at Max Planck Institute for Astronomy. So MaGICC means making galaxies in a cosmological context. So this uses gasoline, some sort of standard things, UV background, star formation. There's Medline cooling, which I guess for semi-analytical models has been standard for decades. But in hydro simulations, often this has only been put in recently, and it actually makes a big difference to the cooling rates. Then the thing that's different about MaGICC than other simulations, I guess, is the way this feedback is done, and specifically this early stellar feedback. So I'll just motivate that in a few slides. So this goes back to the work of Greg Stinson and Chris Brook. So they had state-of-the-art simulations with all the hierarchical merging, the gas cooling, star formation, stellar feedback, and high resolution, because of course if it's not high resolution, then why bother? But these simulations make too many stars, okay? So this is the stellar mass, halo mass relation. This gray region is what you get from abundance matching. The magenta line is what you get if galaxy formation is 100% efficient. And the simulations all around here, right? You make too many stars, and they're usually in the center, and you get these crazily peak to rotation curves, which are, right, this is not the universe we live in. Okay, so the solution is to add more feedback. Okay, so actually, so what they did was that they changed the IMF. It seems like simple that we think Chabry IMF, Cooper IMF is the same, but actually they have different slopes, the high masses, so you get different amounts of supernovae. different amounts of high mass stars per mass formed. They also just increase the efficiency. Still less than 100%, so it's still physical. And then you can drop down, this is just one halo, you can drop it down onto the relation.
Should that be Chabrier instead of saltpeter rather than?
No, seriously, they went from Chabrier to Krupa, as well as increasing the efficiency, and that made a difference.
Okay, Chabrier and Krupa have number of supernovae per unit mass stars formed in Chabrier and Krupa. I've done this calculation. They differ at the 10% level. That's it.
Okay, well.
Okay.
What a lot of people were using in the old days was Scalo. Scalo has very few high mass stars.
Okay, this is the detail. The point is, there's more energy from supernovae. There's more supernovae. So you do that, and it's good at redshift 0, but then you take the abundance matching results, and then it's way off at high redshift. So this simulation just makes stars too early. So the solution is just add more feedback. This time it's adding. So the way the feedback works, well, there's no feedback for before you get supernovae, right? And so what they decided to do is they said, well, actually, there is energy coming off from stars, and we'll put that in, and this ends up giving you a nice reproduction of the evolution of the relation between stellar mass and halo mass.
It becomes semi-limited. It's also it does that. What exactly what you do?
I don't have the slide to show that. But it's in Greg's paper. The point is, you just add more feedback from stellar winds within the first.
The heating rate that goes, the stellar luminosity is coupled directly to the neighboring gas as a heating rate.
So not pressure, just thermal.
Just thermal. So it's an enormous heating rate.
No, but then they probably have to prevent it.
It's allowed to cool. So it effectively ends up working like a photoionization on gas pressure, basically. You end up cooling it. You end up raising everything around the star particle to 10 to the 4K. That's a little more than, it's more than but it's all, but they don't use the cooling turnoff for the early module.
Okay, we're into discussion here.
Let's let Eric finish.
Okay, so that was one galaxy, but so Raul Kanan, who's in the audience somewhere, so he applied this feedback recipe to a big box, cosmological volume, and this is showing the stellar mass halo mass relation at redshifts 2 to 5, and so the simulation has a good agreement in halos below about 10 to the 12, and then, as you might expect, there's no AGN feedback in this model, so there's problems at these high masses. But for what I'm going to talk about, everything is going to be below 10 to the 12. So there are also a few other MaGICC projects. Camilla Penzo will talk next about the effect of dark energy on galaxy structure. And there was a recent paper by Jakob Herquist who talked about effects of warm dark matter on galaxy structure. So now I've introduced MaGICC, I want to talk about the dark halo responses. So this just shows some global properties. Stellar mass, halo mass. There's 31 cosmological zoom-in simulations. The colors indicate the type of feedback. So the fiducial MaGICC feedback is these the red points. So these basically agree quite well with the stellar mass, halo mass relation. The MUGS feedback, which was the one I showed earlier, was the one, right? There's not enough feedback and you make stars too efficiently. So in terms of dark matter density slopes, so this is the dark matter profile as a function of virial radius, and then we're measuring the slope between 1 and 2% of the virial radius, just fitting a power law. And then if you compare this to, say, halo mass, there's just a huge scatter, right? There's a big range of inner slopes. Some things have close to isothermal, so -2. Some things are close to the NFW slope. So this is what you predict based on the concentration mass relation, right? You never actually reach the -1 at this scale. And then there are some halos which basically end up with a core, okay? But you wouldn't use halo mass to predict this. Okay, yeah, so that's just expansion and contraction. So what is causing the expansion in these simulations? So I kind of alluded to this earlier. The basic mechanism is you have a bursty star formation, and feedback drives gas flows, and you get a rapid fluctuating potential, and this causes halo expansion. And this is, I wanted to show this movie which shows the outflows. Okay, so this is a temperature map. So red is hot gas, and you're going to see the hot gas coming out in these bubbles, and then it's just going to collapse back. And you see the star formation is very bursty, like it's just bouncing up and down. Right, so this is the process of the galaxy is kind of just breathing. This is the thing that's constantly putting energy into the halo, causing it to expand. All right. That simulation? I don't know, actually. OK, so, but what we found was that if you plot the inner slope as a function of the star formation efficiency or the stellar mass to halo mass, then there's actually a pretty good correlation. Right? All of the galaxies follow this. Well, this dashed line is just some fitting formula. This gray region is the region which is actually disallowed by abundance matching. Right? So real galaxies probably don't live here. And so what we're seeing is we have this competition between inflows and outflows. And so what's happening is that at these high efficiencies, the adiabatic contraction is winning. Right? There's just so much inflow that this feedback effect is really not doing anything. Then at these intermediate scales, you get maximal expansion.
Efficiency of what?
Huh?
Efficiency of what?
Stellar mass to halo mass. Conversion of baryons into stars.
And this is for the individual galaxy, not the typical mass of.
Yeah, this is for these are for the individual simulations. Okay, and then so something that is sort of would make sense is when you get to very low efficiency, you don't make any stars. You don't have any change to the dark matter density profile. So what scales are affected? I guess I just added this plot because of the previous talk. So the scale that's most affected is basically the scale you want to affect for this too big to fail problem. Right? It's 40, 50 kilometers a second that you make cores, you reduce the central densities by quite a lot. So in the next few slides, I just want to talk about something that I've been doing to try and parameterize the way the halo is responding to galaxy formation. Okay, so we're going to follow a...
0 minutes.
Okay, we're into the discussion. We had a minute there. So we're going to follow a shell of dark matter. And so this F and I means final and initial. And I know people get a bit funny about this. So you can just think of it as hydro and dark matter only if you like. So this is a simulation. These are the mass profiles. The solid is hydro, dash is dark matter only. And so we're going to take a mass shell, okay, and then you're going to measure this R initial. So this is where the dash line, the size where the dash line is, and then we're going to measure R final on the hydro simulation, and then we're going to go and measure the total mass within here. That's MF. And then we're going to measure the total mass within our final for the initial simulation. Okay, so that's how we get these numbers. And then we plot them against each other, and you get this diagnostic for halo contraction. So this diagonal line would be adiabatic contraction. And we find something, this is kind of similar to what Oleg found a few years ago. So this is just another simulation that sort of does a very similar thing. So this halo is contracting, not quite adiabatic. And then another example is a halo that just expands completely in every radii. And then another case where there's basically no change. There's really this is one of dwarf galaxies that basically there is very little. Galaxy formation is so inefficient that you wouldn't expect there to be any change. And then another example is where you actually get contraction at large radii, and then at small radii you get it with expansion. Right? So you basically get all the possible things can occur. But something that kind of links all these things is the efficiency of star formation. Okay, so this is the ratio between the stellar mass and halo mass divided by the cosmic baryon fraction. So when you're high efficiency, you get contraction, and then as you go to low efficiency, you start getting more expansion. As you go to low efficiency, you get more expansion, and then as you get to very low efficiency, nothing changes. So I just got 1 or 2 slides. So
You have a conclusion slide.
yeah. So I won't go into the details of what I've been doing, but some preliminary result is that there's a nice correlation in this plane between the efficiency of star formation and how the halo is responding. So when you're at very high efficiency, and this is not realistic in terms of abundance matching, you get a contraction that's close to adiabatic. When you get to about 20% is what we kind of think is the peak. Then you get something which is contracting a little bit and then expanding. And then for dwarf scales, you get expansion. OK, so I think that's it. OK, yeah. So in summary, galaxies do respond to, dark matter halos do respond to galaxy formation. And what we're finding is it's correlated with star formation efficiency. We're looking at seeing if there's any other correlations. But so basically, if you have high efficiency, you get steep cusps, you get contraction. If the efficiency is below about 10%, you end up with expansion and sometimes even constant density cores. And if you're at very low efficiency, you get no change.
First, I'm not sure why you look for correlation with star formation efficiency, because this is the result. What really makes it happen or not happen is the outflow. If you have a lot of outflow, you have little efficiency there. And if you have little outflow, then all the gas is there, and you make no stars. So I would just put it in a different context.
But the stars are a lot easier to measure. The stars are a lot easier to measure than the output.
Yeah, but that's the result, that's not the reason. Okay? The second thing, is a comment. You don't need this quantum fluctuation to understand the expansion. You can make a very simple exercise, which you alluded to. And you just throw out the gas with impulse very quickly.
That's not efficient enough.
No, do it 10 times. The same way. Many starbursts, slow contraction, fast expanse, fast outflow. You get the same result as that.
You.
I just want to understand the result for forecast stable pattern. So you find almost no impact for very low mass galaxies. And the reason you point out is you have a very small star formation for those halos.
Yes.
So then follow this simple logic. Basically, there is no mass feedback. Because if there were feedback, so you would have an expansion of feedback. But there is no change in density profile. I mean, feedback is also very, very small. So then I would ask about the cold gas interaction. I would
Well, so the thing is that
predict a very high cold gas.
the mass loading factor increases when you go to low mass halo. So even though you convert a much smaller fraction of the baryons into stars, you end up with a lower cold gas plus stars. You end up with less. You end up ejecting more material from the low mass halos than the high mass ones.
You still have a lot of outflow for those low mass halos. Then you would expect a very large.
Well, so the point is, it's not how much mass you eject from the system. It's the way you remove the mass. So if you do it all in one go, that doesn't have much of an effect. But if you move the gas around a lot, then that has a cumulative effect.